Here's a quick summary of how CO2 is carried in the blood. It's carried in three main forms. It can be directly dissolved in the plasma, which happens with oxygen as well, but CO2 is 20 times or so more soluble in plasma than oxygen. So more CO2 is dissolved in plasma than oxygen, but this is still a very small proportion of the overall CO2 transport by the blood. Second option is bound to proteins. CO2 will quite happily bind to any uncharged amino group, so that's NH2, that it can find, particularly on hemoglobin, and it likes to bind to lysine and arginine residues on hemoglobin. Now the Haldane effect states deoxygenated hemoglobin has much greater affinity for CO2 than oxygenated hemoglobin, which makes sense because CO2 is produced by the cells that are consuming oxygen. So if your hemoglobin molecule gets to a place where oxygen is being consumed, it's going to offload the oxygen, and the hemoglobin is then going to have a greater affinity for the CO2, which is helpful. The place the oxygen is being consumed is also where the CO2 is being produced. So you want the hemoglobin to pick up the CO2 and then take it to the lungs. When it gets to the lungs, you want the opposite to happen. There's going to be more oxygen hanging around. You want the affinity of hemoglobin for CO2 to drop so that it offloads the CO2 into the lungs. So you get this nice self-regulating feedback loop. So that's bound to proteins. This also is a fairly substantial amount, but it's still not the biggest contributor. The main way that CO2 is carried in the blood is as bicarbonate ions. And this is the bulk of CO2 transport in the blood. And what happens is CO2 dissolves into water to form carbonic acid. The carbonic acid then readily dissociates into bicarbonate and hydrogen ions. Now this reaction will happen spontaneously, but if you have the enzyme carbonic anhydrase present, then this reaction will happen much faster. Carbonic anhydrase is found inside the red blood cell. So what happens is the carbon dioxide and the water freely diffuse across the membrane into the cell. They then meet carbonic anhydrase. This reaction happens, and this produces bicarb and hydrogen ions. These are charged ions, so they can't leave the cell very easily. And if they're allowed to build up, what happens is you get lots of these building up, and this is going to try and push the reaction back the other way, which is not what we want. We want this reaction to keep going in the same direction. So we need to get rid of these ions. To get the bicarb out, what happens is it gets swapped for chloride ions, and this is called the chloride shift. And the reason it's swapped for chloride is you can't get rid of a negative ion without replacing it with a negative ion, otherwise your red blood cell becomes positively charged. So the chloride, or the hamburger shift, is bicarb out, chloride in, and that maintains the electronegativity of the cell, or the electroneutrality of the cell, and it helps get rid of the bicarb. But we still have the hydrogen to deal with. So what happens is the hydrogen then binds to hemoglobin, and hemoglobin, once it's deoxygenated, is much happier to bind hydrogen ions than when it is oxygenated. That gets rid of your hydrogen ion problem and allows this reaction to progress. And that is how CO2 is carried in the blood. Dissolved in plasma, bound to proteins, but mostly as bicarbonate ions.